Non-inertial reference frame and its implication. Introduction. The non-inertial frame of reference is one of the most fundamental concepts of physics. However, it is imperative to understand these fundamentals of a non-inertial force to appreciate its implication and relevance in the modern world fully. The non-inertial frame of reference essentially implies a form of reference currently or continuously undergoing a motion, acceleration or even deceleration, in a given vector or scalar form of motion. As the Einstein relativity concept explains, this form of motion does not fundamentally obey the provided laws of physics. Instead, a fictitious force should be introduced for the motion to be determined, unlike in the inertial frame of reference, where the point of reference is based on a motionless observer. Also, compared to an inertial frame of reference, it is worth noting that this form of reference does not obey the Newtonian three laws. This is because this form of reference changes with respect to changing velocity. Its frame of reference accelerates or decelerates in an undefined direction of motion. Notably, the law of inertia does not hold in this case since the forces acting on an accelerating observer are fictitious in nature and, therefore, cannot be fully accounted for. One example of this scenario is the force that seemed applied to a passenger in a moving vehicle when it stops or suddenly accelerates. The force felt by the passenger is due to the car's motion and not due to his/her motion. The perceived, experienced force resulting from the car's deceleration or acceleration is, therefore, fictitious. Theories related to non-inertial reference. One of the theories closely related to the non-inertial reference is the Einstein relativity theory. The idea in this theory is based on relativity compensation. There must be precise or accurate measurements to compensate for the accelerated observer, in this case, perfectly. In order to accomplish this, Einstein stated that time, which was usually taken to be constant, was not, in fact, constant and could be added to a three-dimensional location as a fourth constituent. In this case, there is a difference in the reading of the clock as a result of the acceleration of the observer. Time is not constant relative to two accelerating bodies. This effect has been solved by a metric method that changes non-inertial frames to inertial frames based on observations. Importance of non-inertial references. Non-inertial references are essential for several reasons. The most basic reason is that they enhance our understanding of the world based on the essentials of physics. The non-inertial references are based on points of reference that are essential in explaining the changes in the position of a body around the globe and the body's position concerning an observer. This is usually applicable in an inertial reference scenario where all the laws of inertia and Newton are obeyed. In the case of non-inertial reference, a more complex approach that includes a fictitious force needs to be used since this form of motion does not directly obey the laws of physics. Therefore, this point of reference is essential in the world of science, where travel within and outside space is inevitable. As provided by the special relativity theory postulated by Einstein, coordinates and time references coupled with metrics allow scientists to account for the position of an accelerating body. This concept is also important since it opens our minds beyond the normal laws of physics. Non-inertial reference, for instance, helps us fully appreciate that time is not constant as perceived for a long time. Time changes concerning the acceleration of two bodies, a concept called time dilation. Examples of non-inertial references. There are a number of examples that are non-inertial in nature due to the fact that they experience acceleration or deceleration and a point of reference at the same time. A good example in our daily lives is the force we experience whenever there is a sudden deceleration or acceleration of a vehicle when we are inside. We feel the force away or towards our seats depending on the motion of the vehicle simply because of our body's unwillingness to abruptly alter in motion. This, therefore, means that there is no actual force applied to our bodies but only the vehicle's change in velocity. The other example of non-inertial reference, which is actually its application, is the non-inertial GPS multisensory system of navigation. This GPS sensor uses the provisions of the non-inertial reference to mitigate the effects of Doppler errors on body movement and, hence, improve navigation performance. Doppler system equipment usually provides accurate positions during a GPS outage. Conclusion. As discussed in this essay, it has been noted that non-inertial references do not obey the fundamental provisions of physics laws. This is because the point of reference in a non-inertial reference is always experiencing acceleration or deceleration. To account for the force, direction, and position of such a body, it is usually important to invoke a fictitious force to the equation for the moving body to obey the simple laws of physics. One of the theories related to this form of motion is the special theory of relativity, which explains the compensation concept and the fact that time is not a constant constituent as it has been perceived. There are a number of applications of this non-inertial idea. The GPS positioning system, for instance, implements the fundamentals of non-inertial reference.